Water. We use it every single day, right? We drink it, we cook with it, we see it everywhere. But what if I told you that the story of our planet's water is actually kind of shocking? That's what we're diving into today.
Yeah, we've all seen the pictures from space, right? Earth, the blue planet, just this gorgeous swirl of blue oceans. And it makes you think, if there's that much water, then why on earth do we hear about water shortages all the time? It seems like a total paradox, right? So much water, but so many places facing scarcity. Well, to figure this out, we have to go back to basics. And that means starting with the one thing that governs all water on our planet, the water cycle. Think of it as this giant natural recycling system. It's been running for, billions of years, constantly moving and changing water. Let's quickly walk through how it works.
Okay, so first up, you've got evaporation. The sun beats down, heats up the ocean, and turns that liquid water into vapor. Then, that vapor rises up, gets cold, and poof, it condenses into clouds. And finally, when those clouds get full and heavy, you get precipitation. Rain, snow, you name it. The water comes right back down to Earth. It's a beautiful, simple cycle.
And here's the most important part to remember. This whole thing is a closed loop. The water just goes around and around, from the oceans to the atmosphere to the land and right back again. Nothing new is added and nothing is ever really lost.
It's kind of like our planet is a giant sealed terrarium. One of those glass bowls with plants inside. The water that's in there is all the water there's ever going to be. It just keeps cycling. We're not getting fresh deliveries from outer space.
Which leads to this totally wild thought. The water you're drinking right now, it could have been rained on a dinosaur. Seriously, it could have been part of the Nile River thousands of years ago. It's the exact same water, just recycled over and over again.
Okay, so if we have the same amount of water we've always had, then the amount isn't the problem, right? So what gives? Well, here's the first big catch. The problem isn't the quantity of water, it's the quality. Most of it is salty.
And I mean, look at this. It's not just a little salty, it's overwhelmingly salty. 97.3% of all the water on Earth is saline. That means everything else, all the glaciers, all the rivers, all the lakes, has to squeeze into that tiny 2.7% sliver. It's kind of nuts when you see it laid out like that. So what do we even mean by saline? It's just a fancy word for salty. On average, the ocean has about 35 parts per thousand of salt, which is way too much for us to drink. But believe it or not, some places are even saltier, a lot saltier.
All right, look at this number, 340. Just let that sit there for a second. Any guesses what that could be?
That is how many grams of salt are in a single liter of water from the Dead Sea. That's almost 10 times saltier than the regular ocean. It's so incredibly dense with salt that you can just lie back and float, no effort at all. It's a fun fact for sure, but it's also a perfect extreme example of why we can't just drink ocean water.
Okay, so we've got it. More than 97% of the world's water is off limits. So we're left with that little 2.7% of fresh water. But here's where the story gets even crazier. We need to look at what's going on inside that tiny percentage. So here's the big breakdown. You see the oceans dominating at 97.3%. But now look at the fresh water. Out of that small amount, a whopping 2% of all of Earth's water is frozen solid in ice caps and glaciers. Then you have groundwater. And then look at the numbers for lakes and rivers. They're minuscule. It's hard to even wrap your head around those tiny decimals. So let's try a different way. Let's try an analogy. Imagine all the fresh water on the entire planet fits into just 12 spoons. That's it, 12 spoons. So where is it all?
Well, right off the bat, 9 of those spoons are completely useless to us. They're frozen solid in ice caps, gone. Then another 2 spoons are trapped way underground as groundwater. So what's left? We're down to just half a spoon. That little half spoon represents all the freshwater lakes in the entire world.
So, we've accounted for the frozen water, the underground water, and the lake water. From our original 12 spoons, all we have left is one single drop.
And that one drop? In percentage terms, it looks like this, 0.0001%. That's an insanely small number.
And what is it? That's all the water in all the rivers of the world, combined. Think about that. The primary source of fresh water that civilizations have been built on for thousands of years amounts to just one drop in our little analogy. Just let that sink in. This isn't just a cool trivia fact. It's about our very survival. Because at the end of the day, water isn't something that's nice to have. It's everything.
So here's the big takeaway. All of us, every single person on this planet is depending on that tiny, tiny fraction of water. We're all sharing that one precious drop. It puts things in perspective, doesn't it?
So, once you know that almost all the water on our blue planet is either salty or frozen, it changes how you see things. It makes you realize just how incredibly rare and valuable fresh water really is. So, I'll just leave you with this one question to think about. Knowing all this, how will you use your next glass of water?
Today, we're diving into the incredible and sometimes absolutely terrifying power that's hiding in our planet's oceans. We think we know the sea, but every now and then it shows us a side of itself that we could never, ever imagine. You know the feeling, right? It starts with something we all know and love. I found this one description that just nails it. There is something magical about walking bare feet on the seashore, the cool breeze, the music of the waves. Everything is so fascinating. It's a perfect picture of peace. But what happens when that perfect picture turns into an absolute nightmare? This number, over 10,000. That's how many lives were lost in India on a single day, December 26, 2004, when the ocean unleashed its hidden, terrifying power. So to really get what happened, we need to look at the two very different faces of the ocean. There are the familiar waves we see on a beach trip, and then there's the monster that is a tsunami. And let me tell you, they're not the same thing, not even close. So a regular wave, it's pretty simple, really. It's just the water on the surface rising and falling over and over. You can think of it as just a surface level thing, kind of skin deep. And what causes them is usually pretty straightforward, too. Wind blows across the water, and that friction creates ripples that eventually grow into waves. The stronger the wind, the bigger the wave. Simple cause and effect. But a tsunami, oh, that is a whole different animal. The word tsunami itself is Japanese, and it means harbor wave. And the reason it got that name is actually fascinating. Out in the deep ocean, these waves can be really small, almost unnoticeable. It was often only when they reached a harbor and just completely destroyed it that people knew something terrible had happened. So here's the most important thing to understand. It's the difference in their very DNA. A normal wave is just a surface ripple made by wind. A tsunami, on the other hand, is born from a massive geologic event, like a huge earthquake under the sea that shoves the entire column of water from the seabed all the way to the surface. It's not a wave on the ocean, it's the entire ocean itself on the move. So how did this all play out back in 2004? Let's break down the anatomy of that specific, horrific disaster. It all started the day after Christmas. Deep, deep beneath the Indian Ocean, right off the coast of Sumatra, the Earth's crust just violently snapped. The magnitude of that quake was a staggering 9.0 on the Richter scale. I mean, this wasn't just some tremor. It was one of the most powerful earthquakes ever recorded. The amount of energy it released is just unimaginable. Okay, so what you're seeing here is the chain reaction. First, one tectonic plate, the Indian plate, slid under another, the Burma plate. That sudden movement forced the seabed above it to heave upwards by as much as 20 meters. This created a huge void, and the ocean rushed in to fill it. Finally, all that water had nowhere to go but out, and it raced towards the coastlines as a tsunami. An event like that, well, it generates a truly unstoppable force. Now, we're going to look at the terrifying journey of that wave and the just unbelievable scale of its impact. Just to give you an idea of the speed we're talking about, in the deep ocean, that tsunami was traveling around 800 kilometers an hour. That's about the same speed as a commercial jetliner. Just try to imagine that, a wall of water moving as fast as a 747. Now, as the wave got closer to the coast, the water got shallower, so the wave slowed down. But all that incredible energy had to go somewhere, right? Well, it went up. The wave that finally slammed into the coast was up to 15 meters high. That's like a 5-story building made of water. And just when you think that's terrifying, get this. The largest tsunami ever measured was 150 meters high. That is 10 times bigger. It's a humbling, mind-blowing reminder of the power our planet is capable of. The devastation was just absolute. The waves surged up to 3 kilometers inland. It completely submerged Indira Point, which is the southernmost tip of India. More than 10,000 people in India alone were killed. Over 100,000 homes were affected across multiple states. The scale is it's almost impossible to wrap your head around. But this is where the story takes a really tough turn. It leads us to the hardest question of all. The earthquake was a natural event, sure, but was the scale of the human tragedy that came next inevitable? Or could it have been prevented? So why? Why was the damage to life and property so incredibly severe? The painful answer is that a lot of it didn't have to be this way. The disaster wasn't just about geology. It was a failure of systems and, most importantly, a failure of knowledge. It really came down to 3 key failures. First off, unlike the Pacific Ocean, the Indian Ocean didn't have a good system for monitoring earthquakes. Because of that, there were no early warning systems in place to alert people. And maybe most critically, most people living on the coast had no idea what a tsunami was or how to spot one coming. And this right here, this is the crucial piece of information that could have saved thousands of lives. The first real sign of a tsunami isn't a giant wave coming in. It's the exact opposite. The ocean suddenly and rapidly pulls way, way back, exposing the seafloor like you've never seen before. That is your signal to run for high ground immediately. But tragically, without that knowledge, the exact opposite happened. This quote is, well, it's just haunting. It says, "Instead of people going to high ground, they started assembling at the coast to view the miracle. They saw this strange, incredible thing happening and thought it was a wonder of nature, not a final warning." And really, that's the ultimate lesson here. The 2004 tsunami is this devastating reminder that while we can't stop the incredible forces of our planet, our greatest defense isn't technology or trying to build bigger walls. It's knowledge. It's preparedness. Because understanding the world around us, it isn't just fascinating. Sometimes it's the one thing that can save us. Have you ever just stood by the ocean and wondered why it's always moving? You know, it never, ever seems to rest. Well, the answer isn't just in the water itself. It's actually way, way beyond our planet. Let's dive in. So to really get to the bottom of this, we're going to go on a little journey. We'll start at the coastline, shoot all the way out into the cosmos, and then come right back. All to uncover the massive, invisible forces that give the ocean its constant pulse. Okay, so the first and most obvious motion is something we see every single day at the beach. It all starts with the tide. And a good way to think about it is like the entire planet taking one long, slow breath in and out. So what is a tide? Well, put simply, it's this super predictable, twice-a-day cycle where the ocean's water level rises up and then falls back down. It's a rhythm you can pretty much set your watch to. And that cycle gives us 2 things we're all familiar with. You've got high tide, when the water creeps way up the beach, and then you've got low tide, when it pulls all the way back out, sometimes revealing parts of the ocean floor you don't normally see. So you gotta ask, right? What in the world, or maybe not in the world, has enough muscle to move trillions of gallons of water like that? Well, for the answer, we have to look up. Way up. It all comes down to one thing: gravity. The ocean is literally caught in the middle of this giant cosmic tug of war. Both the moon and the sun are constantly pulling on Earth's water. And here's the thing. Because the moon is so much closer, its pull is actually more than twice as strong as the sun's. It's the real heavyweight champion of our tides. Now check this out. A couple of times a month, during a new moon or a full moon, everything lines up perfectly. The sun, the earth, and the moon, all in a straight row. When that happens, their gravity teams up and bam, you get the most extreme tides, the highest highs and the lowest lows. We call these spring tides. But what happens when they're not lined up? Well, during the moon's first and last quarters, the sun and moon are pulling on the earth from a right angle. Now they're working against each other. This cosmic tug of war results in much weaker, less dramatic tides, and those are called neap tides. Okay, so that's the up and down motion of the tides, but there's another much deeper movement happening all the time. The ocean has these massive, hidden rivers of water constantly flowing across the entire globe. These are the ocean currents. You can really think of these currents as the planet's circulatory system, or maybe like giant conveyor belts. They're always moving these huge streams of water in very specific directions, and they have a massive impact on weather and ecosystems all over the world. And these currents basically come in two flavors. You've got your warm currents, which get their start in the toasty waters near the equator and flow out towards the chilly poles. And then you have cold currents, which do the exact opposite. They bring that frigid water from the poles back down towards the tropics. And this is where it gets really cool. These currents are basically the planet's thermostat. Warm currents, like the famous Gulf Stream, carry heat with them. It's a huge reason why London is so much milder than parts of Canada, even though they're on the same line of latitude. And of course, the cold currents, like the Labrador Current, they bring the chill. So you've got these hot and cold rivers of water moving all over the globe. What do you think happens when they smash into each other? Well, the effects are pretty dramatic, and they have huge consequences for marine life. And for us. Okay, so this collision is absolutely crucial. When they meet, it churns everything up, pulling all these nutrients from the bottom of the ocean up to the surface. And that's like ringing the dinner bell for plankton, the tiny organisms at the very bottom of the food chain. This creates an explosion of life, and it makes these spots the absolute best fishing grounds in the world, period. And that right there, that's exactly why places like the seas around Japan and the eastern coast of North America are just legendary fishing hotspots. It's not luck, it's science. It's precisely where these powerful warm and cold currents happen to meet. But, there's always a catch. This exact same collision, where warm, moist air hovers over that cold water, also creates some of the thickest, most stubborn fog on the planet. It can make navigating these waters incredibly dangerous for ships. All right, so we've gone all the way to space and down to the deep sea. Let's bring it all back home. Why should any of this actually matter to you in your daily life? This cosmic pulling and these deep sea rivers. Believe it or not, these forces are touching our lives every single day. High tides, they help huge container ships get into harbors, which affects the price of the stuff you buy. They bring more fish closer to shore for local fishermen. They influence our climate, our food supply, and now, they're even being used for clean energy. Yeah, you heard that right. The power here is so immense, so predictable, that we're actually learning how to harness that rhythm of the tides to generate clean electricity. It's just an incredible way to tap into a completely natural and constant cycle. So the next time you're looking out at the ocean, just remember that constant motion isn't random. It's a dance, and the moon is leading. It's a powerful reminder of all the huge invisible forces that are shaping our world every day. And it really makes you wonder, doesn't it? What other forces are out there, quietly shaping our reality that we're only just beginning to understand?